Hello, I'm Akash Gupta, and welcome to this video presenting our work on hierarchical kinematic probability distributions for 3D human shape and pose estimation from images in the wild. Monocular 3D shape and pose estimation is an ill-posed problem, where many 3D solutions can plausibly explain a given input image. Most previous methods predict a single 3D human, which can yield impressive results given unambiguous images. However, depth ambiguities and occlusions are common in the wild. Some recent methods predict a fixed number of 3D human hypotheses. In contrast, our approach outputs a probability distribution over body shape parameters and 3D joint rotations conditioned on the input image, with which we can sample any number of plausible 3D reconstructions and estimate 3D vertex location uncertainty over the body surface. The distribution prediction network leverages the kinematic tree structure of the body joints and recognizes that joint rotations lie in the nonlinear SO3 manifold. We adopt the widely used simple body model to parameterize body shape and pose. Pose is defined by the 3D rotation of each joint in the simple kinematic tree relative to its parent joint. Simple outputs a vertex mesh given an input shape vector and 3D joint rotations. We aim to predict distributions over 3D joint rotations, which lie in the nonlinear SO3 manifold that has a different structure to the space of unconstrained neural network outputs. A suitable distribution over SO3 is the matrix Fisher distribution, whose parameter f is an unconstrained 3x3 matrix and can be simply regressed by a neural network. The shape and properties of the distribution depend upon the SVD of f, from which the mode rotation, principal axes of rotation, and dispersion about the principal axes may be determined. The latter two model rotation uncertainty. Given an input image, our method predicts a distribution over body shape and pose in 3 stages. First, we convert the input image into an edge and 2D joint heat map proxy representation during inference. This aids the use of synthetic training data with varied random shapes and poses, thus overcoming the lack of body shape diversity in current training datasets. Edge-based inputs have a smaller synthetic to real domain gap than synthetic RGB images, as well as other common input representations, while being computationally cheap and robust during inference. Next, we use a deep neural network to predict distributions over body shape and pose conditioned on the input proxy representation. Specifically, the network first outputs the means and variances of a Gaussian distribution over the shape parameters, as well as estimates of the camera and global rotation. Then, the network predicts matrix Fisher parameters for the distributions over 3D joint rotations. The 3D rotation of each bone in the simple kinematic tree is defined relative to its parent joint. To enable the rotation distributions to match the 2D input, we hierarchically condition each joint's distribution parameter on all its parents' distributions, represented by the parent's modes, dispersions, and principal axes. Finally, we sample 3D simple body meshes from the hierarchical pose and shape distribution with our proposed differentiable rejection sampling algorithm, which employs the reparameterization trick. During training, differentiable sampling enables a loss between reprojected samples and visible 2D targets, in addition to a negative log likelihood loss over the predicted shape and pose distribution parameters. The hierarchical architecture and 2D sample reprojection loss enable the predicted distribution to match the visible parts in the input image, while exhibiting greater uncertainty for occluded regions. In a monocular setting, uncertainty can arise even without occlusion, for example due to depth ambiguity. Our approach achieves state-of-the-art body shape performance on the SSP3D dataset. It is competitive in terms of pose metrics on the 3DPW dataset, outperforming other approaches that do not require any 3D label training images. In summary, monocular 3D shape and pose estimation is an ill-posed problem. Instead of predicting a single solution, our approach predicts a hierarchical matrix Fisher distribution over 3D joint rotations, in addition to a Gaussian distribution over shape parameters, from which we can sample 3D solutions that match the input image via differentiable rejection sampling. Thank you for listening.